An electron enters a uniform magnetic field, B equals 0.23 Tesla, at an angle of 47 degrees relative to the magnetic field. We are to determine the radius of the orbit that it takes in the magnetic field, as well as the pitch, which is the distance between adjacent loops along the helical path, assuming that the electron's speed is 3.3 times 10 to the 6th meter per second. In solving this problem, we need to be aware that the force due to a magnetic field on a charged particle with some velocity is given by the cross product between the velocity of the particle and the magnetic field. The property of the cross product tells us that only the portion of the velocity that is perpendicular to the magnetic field counts. For this reason, we examine our figure very carefully and recognize that this particular velocity vector is not entirely perpendicular to the magnetic field. Instead, our velocity vector of 3.3 times 10 to the 6th meter per second has two components. One component that we can label v parallel is the component of velocity parallel to the magnetic field, and the other component that we'll label v perpendicular is the component of the velocity perpendicular to the magnetic field. The angle of 47 degrees given in the problem is located here. Thus we are able to see that v perpendicular is 3.3 times 10 to the 6 sine of 47, and v parallel is 3.3 times 10 to the 6 cosine of 47. When analyzing the circular part of the trajectory, we'll be using the v perpendicular, and when determining the pitch between the loops of the trajectory, we'll be using the v parallel. Let's begin with the circular part of the trajectory, and we recognize that this particle, even though it is undergoing a helical trajectory, when viewed from end appears to be moving in a circle, and the circle that it appears to be moving in has a radius of r. Uniform circular motion is a force problem. We will analyze this as a force problem by considering this location along the circular path and naming every force that applies. The only relevant force in the entire problem is the magnetic force, and the magnetic force, we often say QVB, but this time we're going to be a little more particular. We're going to say QV perpendicular B, recognizing that there are useful and useless components of the velocity vector. As with every free body diagram, we orient a coordinate system with the acceleration, and indeed, even though this particle has a uniform speed, it is accelerating in a direction that is known as centripetal. When analyzing the centripetal direction, we will find that there is one force in the plus centripetal direction. That one is QV perp times B, and that, as always, there is indeed an acceleration in the centripetal direction. The amount of that acceleration is v squared over r. Notice that in this case it is again v perpendicular, so that we get a perfect cancellation of these two terms, yielding us a radius value of mv perp divided by q times b. Because the particle is stated to be an electron, we know that the electron mass is 9.11 times 10 to the minus 31 kilograms. The v perp was calculated previously. The charge is the elementary charge, 1.6 times 10 to the minus 19 coulombs. And the magnetic field was given to us as 0.23 Tesla. Plugging in all of these numbers, we'll find that the radius of the orbit is 59.66 times 10 to the minus 6 meters. And this solves the first of the two parts in this two-part problem. To solve for the second quantity, the pitch, we need to go back to the diagram and gain a little bit of understanding. The pitch is a distance along the direction parallel to the magnetic field. As we know, any distance will be equal to some velocity times a time period. What we need to do in order to solve this part of the problem is to determine which velocity and what time we would use to make the calculation for pitch. The velocity part is clear, and we've calculated it previously. The velocity we should use is v parallel, that portion which is along the magnetic field itself. If we think for a moment about the time period, we recognize that to measure the distance between two subsequent loops of this helix, we must allow the electron to make one 360-degree cycle, meaning that the time of interest is the period of the motion, and that's something we're accustomed to calculating in the case of circular motion of a charged particle in a magnetic field. Let's do so now. As stated previously, we begin by recognizing that the pitch of the helix is equal to v parallel times the period, and we're going to use our formula from radius calculated in the previous step to solve for the answer. The key in this step is to understand that the velocity perpendicular can be expressed in terms of the period simply by stating that v perpendicular is the result of one circumference, 2 pi r, over each period, and that's a distance over time for velocity. We see that there is a beautiful cancellation from the left-hand side to the right-hand side of this equation, and that will allow us to solve for the period, yielding period is 2 pi mass over charge times field. Finally, we complete the calculation by remembering that v parallel was 3.3 times 10 to the 6 meter per second cosine 47, which when multiplied by the period of 2 pi mass over charge times field will yield to us the final result, that the pitch in this problem is 0.35 millimeters.